I'm gonna shut this door.
And then number 6.
Okay, welcome to the final lecture in machine design. I did a review in my pre-recorded lecture, so we weren't going to be doing a review today. Although if you have any review questions, you can ask them to me if you want. One of the topics I didn't cover very well in this class, and yes, I do recognize one of the reasons why everybody has struggled with the final project is just because I didn't do a very good job of explaining myself, is the power flow through a system. So we're going to do an example. When it comes to power flow, the idea of power flow is, everything has a reason. Everything has, there's always a reason why everything happens, okay? Nothing just happens spontaneously. It always, as engineers and scientists, we can always go back to why something occurred. If you go look at, how a vehicle moves, we know why a vehicle moves. We know the mechanisms that it takes to get a vehicle to move. This isn't something that is, it's not voodoo magic. It's science. Okay. With power flow, a lot of it is trying to understand why things are happening and how things are occurring. Okay. So you have your output, which oftentimes is, something traveling at a certain speed, something absorbing a certain amount of energy, something being given certain values. Okay, you have your input. If we're referring to a vehicle again, your vehicle input is your gasoline. That's the ultimate input. And this is kind of where machine design is a merger between this class and systems and controls, because anytime you have multiple components all working together, it's a system. And every system is a series of inputs and outputs. Okay? And what connects the input and the output is a series of linkages whose job it is to carry the power and transfer from one mechanism to another. Okay? So this is the overall goal. For your project that I gave you this semester, your input is a motor that provides a torque. Your output is a movement. Okay? Now, for machine design in general, and for mechanical engineers, we really only usually deal with 2 types of movement. Okay? For one is your output is a function, your input or output is a function of force and displacement, or force and velocity, because force times velocity is power. Or your input and output are a function of torque and angular displacement, or angular velocity, if you're talking about power again. Okay? And these are functions, which means they are time-varying values. You can calculate instantaneous power by figuring out what is the torque times the angular velocity, or how is the torque times the angular displacement changing with time. Okay, we can figure out these values. This is ultimately, it's power input. Now there are other power inputs. You can have an electric motor, and then it comes into the ultimate power input to that becomes your current and your voltage. You could have a heat input, and then your ultimate power for that is some heat value, or you could have a pneumatic input or a hydraulic input. Yes, okay, mechanical engineers do deal with hydraulic systems, pneumatic systems, electric systems. But a lot of what we're trying to figure out for this class is just these two. Okay? Force and displacement, torque and angular displacement. Okay? So let's do an example on power flow. I wish this marker was better. I just feel like it's on its last leg. Oh, it is totally on its last leg. That was terrible. I don't even care. I'm just gonna leave it there forever. I'm gonna chastise anybody who picks it up. Like, nope, let it lie. So we're gonna use an example of a piston cylinder system, okay? And for calculating power flow, our idea is in a piston cylinder system, you have some kind of input, you have some kind of output. For a piston is constructed such that there is a piston head that is located in some kind of a cylinder. Underneath the piston head, there is some kind of pressurized gas. Okay? Now this pressurized gas could be air. It could be a mixture of combustion elements, such as an explosion that happens when you combust gas. Okay? This could be Mentos and Diet Coke. This could be many different things that create pressurized gas. Doesn't matter what it is. Okay? That's how a piston cylinder system works. Now, this is the ultimate input to your system. Is the change in pressure of this system is going to exert a force on this piston head. Okay? How does that happen? How does pressure exert a force? What is pressure? What's the units for pressure? Newtons per meter squared. Okay, or PSI, pounds per square inch. Okay. How can we take this and get force out of it? Right, because it's a force per area. If we multiply a pressure by an area, we get a force. A pressure acting over the area of the piston head, if you were to take the integral of whatever the pressure it is at every location and do an area integral of it, you'll get the overall force acting on that piston head. If you calculate the average pressure in the entire cylinder, multiply it by the area, you get the amount of force, and that becomes, it's force upward. Now, one of the reasons why this isn't force outward is because, yeah, there actually is. If you go look at it, the pressure is going to be exerted in all directions. It is going to push the piston head a little bit sideways. It's going to push it this way. If you've ever popped the cap off of a soda and seen how the cap flies off, most of the time it flies straight up in the air, but not always. Sometimes it goes and it flies off to one side. Because there are forces, pressure forces that are occurring in all directions. Now, for a piston cylinder, we treat this as if it's all going vertically because of the boundary constraints. This joint here, a joint happens anytime you have two components contacting each other. It forms a joint. This joint between the piston cylinder and the piston cylinder head is a 2 degree of freedom joint. Okay? If we look at it, if I were to take this piston cylinder head and try to wrench it this way, the cylinder head is going to resist that because it's a very tight connection between the cylinder head and the cylinder. Okay? So it's going to give me a moment about the z direction here, if this is our X, Y, and then Z directions. Okay, where Z comes out of the board. All right? It's going to give us an MZ value. Similarly, if I grab on it and I try to pull it this way, it's going to give me a moment about the x-axis. Okay? So we got an MZ. We have an MX value that this can provide. The connection. Similarly, if I wanted to grab this piston cylinder head and pull it in the x direction, I'm not going to be able to, because there's an x directional force. So I'm going to call that Rx. If I wanted to grab this and pull it in the z direction, there's a z directional force that prevents it from going that way too. So there's a z directional force. This constraint here, I call this a 2-degree of freedom joint because we have 4 values that are constrained. These boundary constraints will ensure that there is a sufficient MZ value so that it does not move, it doesn't rotate about the z-axis. Okay? There's a sufficient Rx value so that it doesn't move in the x direction. Now you'll notice I didn't write Ry and I didn't write My. Because if you were to apply a torque in this direction, the piston cylinder head spins. And that's how the connection is set. Now, if that would have been a square piston would have an My value because you can't spin a square instead of a square peg. You know, it just doesn't work like that. But since this is round, you can spin a round object in a round hole. So this is a 2-degree of freedom joint. 2 degrees of freedom means it constrains 4 areas of motion. It allows the other 2. If I were to apply a torque at the top of this thing in the My direction, this thing would begin spinning. It would begin angularly accelerating according to My. Because this joint itself has no way of stopping that. Now, there's friction, but it's not, unless the friction is so much that it doesn't allow it to move. The friction itself isn't, it's not a boundary condition. It's a fixed force value. Okay? So, this doesn't constrain My, it does not constrain Ry. You can also lift this up and down. So we treat this expansion as if it only happens in the y direction. Because Rx, Rz, Mx, and Mz are all taken care of. Anything in there that causes irregularities are handled by the boundary constraints here. And so all you end up with is a y-directional movement. Does that make sense? It is the boundary conditions that define how this can move. I'm not going to erase yet. So, this is one linkage. Now what we're going to do with this piston cylinder head is we got this cylinder head, we got this arm this is rigidly connected to the cylinder head. We're going to go ahead and connect this to a coupler mechanism, and then this is going to get connected to a crankshaft. Okay? So here, this is our crank, this is our coupler, and this is our piston. Now all this is a 4-bar linkage. It's a crank slider mechanism in reverse. That's it. Because you have one mechanism that spins 360 degrees. You have one mechanism that only travels linearly in one direction. That is a crank slider. Okay? So, if I do a force analysis on this component, I'm going to start by drawing the coupler. Why am I doing that? Because the coupler, quite frankly, is the easiest to understand. Now, this is a revolute joint. A revolute joint applies the following boundary conditions. Okay, let's see, let me draw my axes. This is X, this is Y. Okay, A revolute joint is going to prevent my rotation. It's going to prevent mx rotation. It's going to prevent motion in the x and y directions. Okay? Now, if you have a bolt head on your revolute joint, it will prevent it from sliding out in the z direction too. If this is just a round pin, it does not have an RZ value to it. You could just slide it straight out. We're going to assume that it does have a bolt head and a nut on the other side. It's basically sandwiching the joint. And for that reason, we're going to be able to apply an RZ value. However, can we rotate it about the z-axis? This is my pin. Am I going to be able to rotate it like this? This is my pin. Here's my linkage. Can I rotate my arm like this? Sean's giving me that eye. Is this a trick question? No, this is actually not a trick question. All of these other elements are constrained. But I do not have an MZ value that's caused by this joint. Okay, there may be friction. Friction would create an MZ value, but it is not itself a boundary condition. It's a friction. Friction happens if you provide a moment large enough on the friction only serves as a power loss, not as a boundary constraint. Here, if I apply a moment in the y direction, this my value, as long as that joint has any integrity, it will prevent an my rotation, a rotation in the y direction. It will also prevent rotation in the x direction. As long as the joint has integrity, it will prevent all 5 of these motions from happening. Okay? So that is what a revolute joint is. And this is why a revolute joint is considered a 1 degree of freedom joint. You can have revolute joints again that are 2 degree of freedom, and the only thing is if there's no bolt head on this, I can slide my hand in the z direction. Okay, but putting a bolt head, putting a nut on the backside means that the grip it's stuck on there. Okay, so this is 1 degree of freedom. Now the question here is, because the joint itself does not create a boundary condition in the MZ direction, if this component rotates in the z direction at all, it is not because the joint is creating a boundary condition. It's because, well, other outside external forces are doing that. Okay?
Is that the crank?
Huh?
Is that the crank or the coupler?
This is the coupler. I mean, we can look at this one has a 1 degree of freedom joint at the top of it too. So we can look at it right there also, but I'm looking at the coupler because I'm trying to drive towards the point. We're going to step back and look at the crank. Well, we're going to step back and look at the piston next. Okay, so now what I'm going to do for this is I'm going to go ahead and draw all 5 of those components on here. Because it can carry our x, because it can carry our y, and I'm going to go ahead and call this 1 just because this is the bottom. It can carry an mx, it can carry an my. We're going to go ahead and apply an RZ value to it. Again, I'm going to put 1s on all of those. We can have all of those forces present. Okay, if something happens where you have a little bit of vibration in your system, you'll probably see all of those present. Any kind of vibrations is going to cause this whole system to flex a little bit, just twist a little bit. It happens. There will be minute values for each one of these. Okay? But the one thing that we do not have is an MZ. And we can similarly apply the same forces up here. Our x2, our y2, mx2, my2. And RZ2. 5 forces. Well, 3 forces and 2 moments. Okay? Those are all of the possible forces and moments that can be carried by a revolute joint. Okay? Any questions on that? Those are all the possible forces we can have. No questions? Okay. Now I'm going to skip all of these equations because if we're looking at my, well, you have my1 equals my2. There's no other way for this to generate a y-directional force because these two are aligned on the axis. There's no torque. Yep. Now, it is possible to have an mx value, and that mx value would happen if you have an RZ. We're going to assume that there is no RZ value because there's nothing here that's creating a force in the z direction explicitly. I mean, you'll have some based on vibrations, but it'll be small. It's small enough that we're going to ignore it, okay? So here, we know RZ1 equals RZ2. We know my1 equals my2. mx1 exists if RZ1 works. I mean, we can really start knocking down each one of these because whatever happens here is a result of what happens here. Okay? But we have an interesting thing when we go to do the sum of the moments in the z direction. Okay? Sum of the moments in the z direction is equal to, do we have an mz here? No, because this joint cannot carry an mz. Do we have an mz here? No, because that joint cannot handle, you can't carry an mz value. It's not going to transmit any mz. Okay? Do we have any moments in the z direction? Well, we do. If you take the sum of the moments about right here, the sum of the moments is equal to the length of this component times Rx1. So if we're taking the sum of the moments about this point here, do we have anything else that's going to create a moment in the z direction? Sean says no. What do you think, Daniel? No. If we have an Ry value, the Ry values are in line with each other. When they're in line, it doesn't create a moment. When they're out of line of each other, which is what your Rx values have, then it can create a moment. So what we're dealing with here is Rx, this is equal to 0 if we don't have any angular accelerations. So if this component is statically moving or is moving at a constant velocity, angular velocity, etc., this is equal to 0. And in fact, in machine design, we're going to assume that the accelerations are small enough that that's pretty much always going to be equal to 0. Now, if your components are moving really fast, then it no longer equals 0. This ends up equaling an IZ, alpha Z. But for the sake of this, we're assuming that alpha Z is so small that we don't need to consider it, okay? It does make the math a lot easier. Knowing this, our D value is not equal to 0 because we have a finite length for this component, which means our Rx1 has to be equal to 0. Okay? Rx1 equals 0 because we can't carry a moment here. Well, we know right here, Rx1 is equal to the negative of Rx2 if they're both pointing in the same direction. Otherwise, they're equal to each other. If we know that Rx1 has to equal 0 because there's no moment. We also know that Rx2 has to equal 0, which means because this component only has 2 revolute joints, it can only carry a force that is axial to that component. Which means the total net force transferred through this component will occur along its axis. Okay? I've said this before in this class, but this is the reason why. It's because if you calculate all the forces and all the possible forces it can generate, it is impossible to balance your z-directional moment if you have any Rx value. Okay? So knowing that, we then know the orientation of the force exerted by the coupler on the piston. Now I drew this so that it is straight vertically. Okay? What that means is I know my coupler exerts a net force in this direction. I do not know what that is. I don't even know it could be compressive, it could be tensile. I don't know yet. But I do know that it's in this direction. That is the direction of the vector. I have a 1 in 2 chance of being right, because it could be either down or up. The math will tell what it is. Okay? But this is the coupler. And this is the total force that is being carried through the coupler, has to be in the vertical direction. Okay? Now we're going to take that knowledge, because this was our easy component that only has 2 joints, 2 revolute joints. That one's the easy one to figure out the vectors for. We're going to take that, we're going to go back, and we're going to look at our piston cylinder head, or piston head. Keep calling it a cylinder head. It's either a piston head or a cylinder head. You pick one. The force being exerted by the coupler, well, the way I have it drawn right now, it's in tension, will be pulling upward on the piston head. Okay? That's just the way that I have it drawn right now. Now, this piston head has a pressure down here. We're going to assume it also goes upward. Okay? We can sum all of that pressure by integrating it over the area and come up with a net force in the y direction that's being exerted on the piston head. Okay? And we're going to go ahead and call that Fy. Okay? Now, just looking at the force transfer here, Newton's second law, sum of the forces are equal and opposite. Well, is equal to 0. So here if we sum forces in the y direction is equal to Fy plus, I'm going to go ahead and call this F coupler. And we're specifically looking at the y directional component of the F coupler. Okay? Now, F coupler only goes in the y direction, so that makes it nice for this calculation. I'm going to break that pretty soon. This is true, which means that your Fy, well, I drew this F coupler direction wrong, so it's just going to be a negative. Your F coupler y is equal to the negative of Fy. I guess I should switch that around. Okay? The force that is the input force that's being brought into the system is being transferred through the piston head into the coupler. And we can figure that out using Newton's law. Okay? Now what happens if instead of having the coupler vertical, what if I switch up the system and the coupler is now at an angle? Well, the reality of the situation is this still has to be true. This doesn't change. So is the actual force carried through the coupler going to be larger than or smaller than this value? This coupler can only carry a force along its axis, right? This force has to be Fy in the y direction, which at this point is actually pointed like this at the coupler. Is the actual coupler force going to be larger than or smaller than Fy? Why do you think smaller than?
Because it has an X and Y component to it now. You only take the Y component.
Sean says larger. All right, you guys have to fight now. I want to see fisticuffs. It's a clean fight. First person to bleed loses. Oh, wow, I just put that online. No, these students are not actually fighting. That was a joke. Oh. I need to watch my mouth. Okay, so your argument for why it's larger, why is that the case?
Because the Fy of the coupler is one of the components of the actual force, and that component has to be the same of the Fy coming from the piston. So if we add the two components, it's going to be larger in the actual.
Okay, now the way that you explained it, I like that explanation. The thing is, this force, if we're going to exert it in the same direction as the coupler, is going to be like this. I guess I'll draw it the right way. It's downward, okay? This is the y component. This up here is the x component. These two have to be perpendicular to each other because x and y directions are perpendicular to each other, okay? Which means when we draw our triangle, x and y have to be perpendicular. Because x and y have to be perpendicular, that means the actual value, F coupler, is the hypotenuse to that triangle. Is the hypotenuse bigger than both of the legs? Yes. And that's always true. So yes, I understand your reasoning, and yes, that is, I mean, it makes sense. It makes sense that you would lose some force, right, by switching the angle, but that's not actually the case. It's the opposite. You increase the force in the coupler by having it be at an angle. Yeah, this is the point where everybody's like, pfft. No, it's true though. The higher the angle is for your coupler, the larger the force is being transmitted through your coupler just because of this. Because it can only carry an axial force. Which also means, typically, that the higher the force that's being transmitted through the coupler, the faster this component begins spinning. Which means your alpha value tends to become larger, which means this tends to become more significant the higher the angle is, okay? So, there is a caveat there. While the force does increase, if this mechanism is not moving, the force increases substantially. If the mechanism is moving, it no longer has that same transmission just because there's inertial resistance, which is actually nice because it limits the amount of force that gets transferred. Okay, but this is another reason why power transfer is such a complex system. So, with this not moving, the most critical situation occurs, well, with the force transfer, the most critical situation occurs when you do not have any of that energy going into momentum, transfer, inertial change, whatever. So that's why I had you calculate your system not moving. The forces are the highest at that location. Okay? If your coupler is horizontal to your piston, you have infinite force transfer that's theoretically happening in your coupler. You have an infinite amount of force because the vector has to be in this direction and all of your force is in the y direction. So yes, the math does break on this. You have to be careful on that. So don't put your coupler at a 90-degree angle to either your rocker or, well, no, you can have it to your rocker. Yes, don't do it to your slider. Because, and try to fix it, because it does create an infinite force situation. In any case, we now know this. Now the total F coupler value, I need an eraser. The total F coupler value, the amount of force that's being transmitted through your coupler, okay? As we said, it is larger than the y component value. What that means is we know x and y have to be perpendicular to each other. This has to be the hypotenuse. For that reason, if we know this angle here, theta, then we know that F coupler times the cosine of theta is equal to the y component of the F coupler force. So if we want to solve for F coupler, since we know what the y component is, it's equal to Fy. If we want to solve that, we have to divide F coupler y by cosine theta, okay, to get the total force that's being transmitted through our coupler. All right, and because cosine of theta is never larger than 1, this is always going to be greater than F coupler y. And yes, it does have, because cosine of theta is equal to 0 at infinity, yes, it does create that weird point where technically you can have an infinite force transfer. Just don't calculate the force at that location, okay? All right, now we know how much force is going through the coupler. That is this value right here, F coupler. And we know that here, if we were to model this force over here, okay, then what we have is, first of all, this is a compressive force now. I'm going to go ahead and change this to being in compression. The actual force, F couple Y, is coming in at that angle, because that's the angle that the piston head meets the coupler. The x component of that force has to be perpendicular, so it forms a triangle that looks like that. Okay? This is the hypotenuse. This value and this value are identical. They're equal and opposite. Newton's third law. Okay? Does this make sense? How I drew this. I had to rotate it a little bit because my coupler isn't vertical over here. All that I did was I rotated it this way. And when I rotated it this way, I rotated all my forces with it. Okay? Now that I know this, I'm going to go ahead and call this top one F crank. Okay? If I just do a quick force analysis there, well, first of all, this component's going to be in compression. So F crank, probably it better be negative. Otherwise, they're both pointing in the same direction. Sum of the forces in the y direction is equal to 0 because we're going to, again, assume it's not accelerating or that the accelerations are minimal. And that is equal to your F coupler minus your F crank. So all that means is F crank is equal to F coupler, which is equal to F coupler y divided by cosine theta, where F coupler y is equal to Fy. So it's equal to Fy divided by cosine theta. I have really bad problems with focus. All right, we have one more linkage we need to calculate. The ultimate output of this system is a torque occurring about this crankshaft, where it travels 360 degrees. Okay? This is the exact opposite of the systems that you guys are designing. The systems you're designing, this is your input, this would be your output. I'm flipping it on this one. Okay? So let's look now at the crank. Here, the crank is in this orientation. Okay? It experiences a coupler force. And we're going to call this, I'm going to call that theta 2. You can measure theta 2 relative to here. You can measure it relative to the vertical. I don't care. It'll change your trig a little bit, but I don't know. I'm just doing it relative to the vertical because I have a sense of whimsy today. Okay? And this is F crank. Okay, I've oriented my piece in this direction. Now the question that I have is, this is a revolute joint, this is a revolute joint. But I know I have a perpendicular component here. As we talked about with the coupler can't handle any perpendicular forces, transverse forces. Why not? Because there's no MZ value. This is an output linkage. Okay? Your crank is, if your crank is simply allowed to spin on that axle, it's going to start rotating really fast. Because it's exerting an MZ value on this. This perpendicular component right here is going to create a torque about this axle. It has to. So if we just treat this like a revolute joint, our math is now blown. We have to recognize it's going to accelerate. Or we have to recognize there's an output torque. The output of this system is a torque. There is a torque being exerted on this pin. Now, more than likely what's happening is your crank is probably going to be welded to an axle. It usually is. If the crank isn't welded to the axle, if it's allowed to just spin, there's no reason to even have a crank. Okay? So we will have an MZ value here. And that MZ is going to be your output. That's what we're calculating for doing this whole power transfer. Is we're trying to figure out how Fy creates MZ. And how big is the value of MZ? That's all we're trying to figure out. Okay, we know what the crank distance is. I'm going to go ahead and call this D crank. That's the distance between the two revolute joints. Okay? I'm going to figure out what MZ is. Now, MZ is, in fact, a revolute joint. But it is rigidly welded to an axle whereby the torque can be carried through the axle. The joint itself creates Ry, Rx, Rz, My, Mx values because it is a 1 degree of freedom joint. But we're transferring torque out of that by rigidly connecting this crank to an axle. Does that make sense? So even though this is a 1 degree of freedom joint, we have all 6 forces potentially present. I think that's one thing that people get hung up on this project is when you go to calculate it, there is a torque value or there is a force value that you don't get to see. Here, we don't get to see what's creating MZ because that goes into an axle. This becomes the input to another system. where that torque put on the crank shaft now is converted through gears, gearing output through the wheels of your vehicle. Okay? This isn't the final destination. This is just one section of it. This piece here is only a small system in the overall power transfer of your powertrain. Okay? So, let's figure out what is MZ. Well, MZ, you know what? Let's just do the sum of the moments in the Z direction. Let's cut right to it. Yes, there's going to be an RX value. Yes, there's going to be an RY value that are exerted at this joint. It has to be because F crank has both an X and Y component to it. I don't even care about those. Those are boundary conditions. Okay, boundary conditions, we increase F crank, both RY and RX increase substantially. I don't care about those aren't my outputs. The output that I do care about is MZ. Okay, so I'm going to calculate MZ. Now I'm going to again assume that this component is not rotating, or at least that its rotational energy is small, very small compared to the forces. Okay, so this is equal to, now the way that I drew MZ is negative, and the way that I drew F crank is actually positive. If we're doing the sum of the moments about this shaft right here, this is equal to F crank in the Y direction, which is the perpendicular component, multiplied by the length of that crank. That's going to be what the moment is created by the crank. Now, if this crank, F crank, was exerted along this axis, MZ equals 0. Because there's no moment created by a force that is axial here. The maximum moment occurs when F crank is perpendicular to your crank. So that happens. Now this crank is going to rotate 360 degrees. So you're going to have F crank, the angle between F crank and your crank is going to vary from 0 to 360 degrees. You're going to have every single value at some point in your system. Okay? We're only looking at it a one-time incident because I want you to know how to do this at one time. Okay? And at this specific time, F crank has this specific orientation. F crank Y, by trigonometry, is equal to F crank times cosine of theta 2. Okay, and that's just by the way I oriented theta 2. If you took theta 2 right here, it would be, this would be a sine instead of a cosine. Okay, so I can plug this into here, solve for MZ, and my MZ, which is the output of the system, is equal to F crank Y times D crank, which I can replace this as this. I can replace F crank by this equation that I came up with earlier. It's all good. I'm sorry, I'm running a little long. And when I go ahead and write this out, the output force Fy divided by cosine of theta times cosine of theta 2, because of this, times D crank, and that's it. That's my output force. All right, I have to figure out where I just lost sound. The rest of you guys are dismissed. Kenny, I'm gonna try to fix this real quick so that I have a video with some sound at the end. Hey Walker, I just texted you. If you guys have questions on your paper or while going through this process, let me know. I'm willing to give you guys a little bit of extra time. I don't have to turn in grades for this class until December 4th. So if you need more time than just Monday, okay. Just please don't hand it to me on December 4th.
I have a question.
Yeah.
So, since I only have forces on my crank and my coupler, then would this be my output force, or that would be my power?
Let me end this live stream real quick. Okay. Sorry. Then I'll answer that right away. This is your final equation for the output. It's mz is equal to fy over cosine theta times cosine theta 2 times d crank 2. If you want to increase your mz value, you increase your d crank. The longer the crank is, the more moment is being exerted output. You want to increase here, theta is going to change between maybe 0 and 70 degrees. You can adjust the geometry to limit what theta is between for your coupler. Cosine theta 2 is going to go between 0 and 360 degrees. So there's no way for you to really change theta 2. That's just going to happen. Your power transfer is going to occur because your crank is spinning 360 degrees. So looking at MZ, increase crank value, change, try to get theta to be closer to 0 degrees. Try to center that around 0 degrees, which by the way, most people who create pistons will have their crank, their coupler here will go between these two angles because you have maximum power transfer out of that. And then lastly, yeah, increase your Fy value. So it's the end of the lecture. Thank you. I'm glad that I didn't miss too much on this lecture. Okay, bye. Good luck on your final. You can hand in your paper late. Just don't hand it in too late. Bye.